So let's talk about analysis of things using vectors. And I'm going to use displacement as a good number of examples, but these same techniques could be used with any vector. It could be, again, force, a push or pull, or speeds, or velocities, I should say, movement in one direction or the other. Let's just say that we are taking a stroll and we walk to the east 10 meters, and then we turn around and walk to the west 6 meters. And we could ask, well, what's your overall displacement? Well, if you go 10 to the east and 6 to the west, you're going to have gone really just 4 to the east, right? It's a subtraction. It's pretty straightforward. But we can represent that with vectors, and there's a very special way to do that. And if we learn it in this simple context, then we can apply it to more complicated scenarios. So we call this adding vectors. So we take the two vectors that we realize, and of course those, these vectors though, they correspond with the physical scenario, right? So we have a person, they walk 10 meters, and then they turn around and walk back 6 meters, and they end up here at x equals 4. We know that to be true. What we'll do is we're going to call the first part of the trip, they call it the leg, the first leg of the trip, we're going to call it vector A. So vector A is 10 meters east. Now, when we do cardinal directions, that's fine, but we have to also realize and still assign mathematical directions. We have to decide, okay, well, if east is this way, is it positive, is it negative, what's going on with the direction, so I can assign mathematical values to the quantity. And by the way, the quantity of any vector is called the magnitude. So the magnitude of this vector is 10 meters, and it happens to be going to the east, because a vector is a measurement that has both magnitude and direction. Oh yeah. So we can draw that arrow, right? So this person walks, and you know what, let's do it in red. 10 meters to the east. So this person walks 10 meters to the east. And that would be my vector. That would be vector A. And then they walk backwards. Now that's a different vector. And so they're going to walk 6 meters west. Again, we're going to call it east. We're going to call that positive. We typically call north positive. We're going to match it with the XY coordinate plane. Well, 6 meters west. That would be my blue vector. Now, my blue vector starts at this position and ends here. So note, the blue vector will go like this. I'll call that vector B. The tail is the start of the vector, and the head is the end of the vector, and that represents change in position in this change of position in this particular case, or it could represent the direction of the velocity, or so forth. So we are moving in that direction, and we turn around and move this direction. Well, you'll know when you go 10 and go back 6, you end up subtracting the vectors, or not vectors, so you end up subtracting the values, you end up with a resultant of 4. Resultant. That is the term used when we take vectors, analyze them, see what's going on with all the vectors, we look at them all, and what's the end result of those vectors interacting. And typically, that resultant is found by what we call adding vectors. So that's what we did here. We added vectors. We took vector A and we added it to vector B. Now, that happens when you take the first vector and then you start the second vector at the head of the first vector. They call this method the head to tail method. Now if I draw this off to the side instead of in the picture here, we take vector A, that'll be here. That, and then when I say vector A, we know that's the 10 meter east. Vector B, I could draw over here. That's the 6 meters west. Now they're not together right now, they're separate, right? I can walk 10 meters to the east, and on a separate day I could walk 6 meters to the west. But when I put it in this particular scenario and say, oh, I'm gonna walk 10 meters east, then turn around and then come back 6 meters west, you take those two vectors, you take one, you anchor the one vector, vector A. I'm then going to draw vector B, connect it again, what we call a head to tail. So basically I'm going to start vector B on the end of vector A. The head of vector A is the start for the tail of vector B. The result of all this interaction is from the beginning of the first vector to the end of the last vector. But that direction matters. You're going to end where the end of the daisy chaining of the vectors that happens. That's right here. So that's going to become the head. So again, the tail of the resultant vector starts at the start of the problem and points to wherever the end of the problem is. They call this, a lot of the times, vector R, the resultant. And that resultant, as you can tell, is going to be 4 meters east. And again, that direction is important. And you can do this without doing any math at all if you just do good measurement with some rulers, some proper scaling, maybe even some graph paper. I could have drawn this, I could have said it's worth 10, I could have drawn this as worth 6, put them together, and then if I measure this resultant, it should be equivalent to the 4 units. This addition, this is what we call graphical addition, and it's done head to tail. Now, this particular problem was done all along one axis. You can do addition analysis, head to tail analysis, when you're not along the same axis. Matter of fact, you don't have to be on an axis at all. So let's go through one of those. Let's get rid of this.